The focus of this video is to help you utilize your Excel spreadsheet to solve a lot of problems, especially in spectroscopy. In particular, I want you to understand that there's various types of spectroscopy. What you're doing in the lab is UV-Vis spectroscopy, but I want to just show you it has a crossover to a lot of spectroscopy. And the key to running spectroscopy is to understand that you need to make a good calibration curve. And the fundamentals here are that, as this Pasco spectrometer shows you, there's a light source on one side, it passes through a sample, then it's read on a detector. We read absorbance, and we know from experience that when you read at the right wavelength, where the chemical is photoactive, then you'll get a peak based on how much concentrated the sample is. And if it was more concentrated, you'd see the absorbance increase. And this is a common theme. And so what you need to do, though, is correlate that given absorbance with a set concentration to see if it's a linear relationship. And quite often it is, and you should know going into the lab, you can, whether it is or not. So you know that it's in UV-Vis spectroscopy when you do concentration versus absorbance, you know that it is linear. If you had done concentration versus percent transmittance, as we did in lab 1, you know that it is not linear and it has to be changed to absorbance. But that's not the only analysis in chemistry that we use the exact same techniques. Here we're doing a kind of a type of absorbance, but we're analyzing for metals. And we're exciting these metals first in this flame, and then we pump the metal ions into the flame, and the flame basically has, for example, hot copper ions flying around in there, and then we actually have high voltage light sources that are filled with gas, so you can dial in whichever light source you want depending on the metal you're analyzing. So let's just say that this bulb excites copper, and so now there's a light that's created by excited copper ions. So we know that the light that's being created is very specific to being excited by copper, and that light passes through this ionized flame full of copper. So you can imagine the light then disappears based on how much copper is present, because it will obviously do absorption of that light because it's excited copper ions. But once again, the concentration of the material that's in this flame, if it's high, it's going to absorb most of the light. If it's low, it's going to absorb less. Same idea. Low concentration, low response, high concentration, high response. And you could even do a variation. This is a thermal conductivity detector on what we call a gas chromatograph. So there's a coil inside this chromatograph that separates the different materials, but then the materials get ionized and passed. Then the materials just get passed over these hot filaments, and in one case you just pass the gas, a reference gas with no sample over the filament, and there's a set conductivity through that element. But then as the sample starts to get introduced over the filament, the resistivity of the wire changes. So it's going to respond in some way. If there's very little sample in there, it's going to have a resistance that's going to build up a little bit. But if there's a lot more sample, it's going to build up a lot more resistance. And basically what you do is set a current and a voltage, and the resulting resistance that it's reading out to you is based on the concentration of sample that's touching the filament wire. And once again, we're going to set up a calibration curve. We're going to have known concentrations. We're going to get a known response. And you might just say, well, why don't we just use these these points? Because then I could just use ratios, right? And that would make sense. If I have a set concentration at this voltage or resistance and a set concentration at this greater amount of ohms, then you have a relationship that will basically tell you how the ohms varies with resistance. The problem with that is there's other effects as things get very concentrated where the molecules themselves start to interact with each other. So consequently, then the trend breaks linearity, or if you get to very low concentrations, the instrument parameters might change. Long story short, the way that we do this, the traditional way you do it, is you just analyze concentrations over and bracket the concentrations where your unknown is found. So you don't know the known concentration, that's true, but you know if its responses, for example, fell between these two peaks, then I could keep give me a couple more peaks above and below, and I'll actually be able to prove to you in the area at which I'm analyzing the unknown, I know that this thing is linear, and that's kind of the standard, at least 3, which is not really very good, but 4 or more samples at different concentrations that bracket the response seen by the unknown will be appropriate to set up a calibration curve. And that is really the step 1 of the kinetics experiment, is you're just setting up a calibrations curve. So what I'm going to do is I'm going to jump away from this PowerPoint presentation, and I'm going to look at, I'm not going to save this, I'm going to look at some data that I've gotten from a student, and what we did is we had a stock, this is crystal violet is what this is, and so we figured out based on the percent by mass what the actual molarity of the crystal violet is. And so I'm going to show you how to set up a calibration curve. And so we're going to say, all right, this is crystal violet concentration. We'll just abbreviate that. And then we have it in molarity, so we have our good units. Now, they took the undiluted stock. They got an absorbance on the instrument of 0.45. Then they diluted it down, so you're getting less absorbance, less absorbance, less absorbance, less absorbance. And as long as our experiments run within this absorbance range, and they do, because here's the experimental data that came in off of the instrument. This was done with the spectrophotometer. You can see it started at 0.45, so that's fine. It would be better if it's a little under, but that's fine. We're starting at the absorbance that's within the calibration curve, and we're going to run this experiment. The crystal violet is reacting with sodium hydroxide. The crystal violet's going away, and we're going to figure out the kinetics of this. So you can see the absorbance dropping, and we stopped recording data at 0.19. And if you'll look, we're gonna set up calibration well below that. So we bracketed the place in which we're going to run the experiment, so that's important. So now we're going to see if this literally is linear within this range, because maybe this is too concentrated and the molecules start to interact with each other, and that can change how the light is absorbed, or it actually changes some of the refraction properties. So I want to just show you the power of the spreadsheet to do this. So here's my objective. The first thing is I want to show you how to set up your concentration curve and prove that it's linear within the range. And then the second thing is, if you have that concentration curve, then what we need to do is we need to graph the kinetics experiment 3 different ways. We actually need to know the CV concentration, so I'm going to just abbreviate that. It's going to be in molarities. It's going to be in molarity, sorry. So I'm going to just bracket in the square box, which is understood to mean molarity. I'm going to put in CV, I'm going to bracket it. And so we know from experience that if you'll, with kinetics, that if you'll graph time versus the CV concentration, it's linear, then we know that the crystal violet is actually in a 0-order relationship with time. And if we want to check that maybe it's in a 2nd-order relationship or a 1st-order relationship, we need to graph the log of CV versus time. And if it's in a second order relationship, we would graph 1 over CV versus time. And I just want to show you how to do all this on your spreadsheet. Minimize errors by trying to rewrite or do calculations by hand. And you'll really appreciate the ease with which this happens on the spreadsheet. So here we go. Let's start with just the dilution. Well, the undiluted stock is this concentration. So I'm going to just put that in there. And anytime in Excel, when you start off with the equal sign or on sheets, that signals that you're about to program. And if I just point and click at this cell, it's going to actually take that number. And once again, this is why I talk to you that you don't want to drag units down, because the Excel needs to see all these columns as just numbers, so I don't want to have any letters in there, or it'll try and turn it to text. Now, look at how this was diluted. It took this original concentration, I took 5 mils of it, diluted it to a final volume of 10. So rather than trying to do that on my calculator, I'm just going to let the Excel do it for me, and I'm going to start again with the equal sign and signal that I'm going to actually work on this. I'm going to multiply it by the 5 mils that were added. I'm going to divide it by 10, and while I've got the original, I've already have the dilution concentration done for me. So I'm going to follow that same logic and say, well, this is 1 mil of this sample. So I'm going to click at that. It's that concentration. I'm taking it times 1. I'm dividing it by 10. And once I hit enter, it's going to actually work on that. And if you, so I'm going to hit enter. And so there's the resulting concentration. You can see the result here. But if you look up in this formula bar, it will remind you what the actual calculation is. So now, if you look at this dilution, it had a little bit of a variation where they actually took, it looks like 5 mils of sample 2. So that's actually sample 2. So that's right here. There's see line sample 2. I'm going to take that concentration. I'm going to take 5 mils of it, and I'm going to divide it to a total dilution volume of 10 mils. And the last line is same idea. I'm going to take solution 2. I'm going to take 1 mil, divide it by 10. Now I've got all the concentrations. Yeah, and just to be neat in here, a lot of times keep it in scientific notation, and then you can, and I don't know why that last line didn't grab it, so I'm going to just tell it to get in scientific notation. And then at this point, you can also put the number of significant figures you have, and the original one had 3, so all these have 3, but if you needed more, you can, or less, you can just click it there and get more or less. Keep in mind, it doesn't round, or it does round for you, and you're the one setting this. It doesn't count significant figures in the calculation. So now we're ready to see if this is linear within the range. So what we need to do is we need to graph concentration versus absorbance. All right. So what we're going to do is we're going to insert, and I'll just get all this good information. I'm going to insert. I'm going to pull down. I'm going to do a scattergram. I don't want any lines in there. All right. So here it is. I can clean this up so it looks nice by formatting. Add some chart elements, add axis titles, the primary horizontal. Again, we want it to be proper. This is get all my points for lab and say, okay, this is supposed to be CV concentration, and I can do it one or two ways. If I put brackets around it, it's assumed in chemistry that that means concentration of in molarity, so that is appropriate. It has what I'm measuring and the units, so this is kind of unique. Or I could have put CV concentration, and then off to the right in parentheses I could have put big M for molarity, and then I'll add my vertical axis. Clean that up, and this is absorbance. And absorbance is an interesting measurement. It's actually unitless. So sometimes, just to make sure that I keep with convention of trying to add some flavor of units, people put in what we call absorbance units, which is just kind of a placekeeper. And then of course the title of what I'm doing. You know, this is the calibration curve for CV, and then I might put instrumental parameters, what spectrophotometer I used, my name, the date, that sort of information. That's important. All right, so let's get to the matter at hand. Now I'm going to see if this curve is linear enough, and the way we do that is we grab the series. We're going to add a trend line. And we are going to have a linear trend. We're looking for a linear trend. We just don't set the y-intercept at 0 because the y-intercept is what the numbers tell us it is. We know it should be very close to 0 in a lot of these cases because we know if there was nothing in the water, the absorbance should be 0. But we're not going to force the data through that. But it'll be interesting to look at what the y-intercept is and then make sure you displayed the r squared value. And once you put that in place, you now have the equation for the line. And this is a fairly good calibration curve for, you know, first go around. But I would get in the habit of doing these immediately in the lab. And if this is done correctly, and I look at this and I could say, well, I might want to clean these up. I might want to redo these, you know, these two data points and see if I can get closer to 0.99. But for our purposes, we're just going to keep moving. And then what we're going to do is we're going to now use, this is the important part, and oh, another thing I would point out is that y-intercept is very close to 0. It's 0.0139, so it gets really close to 0, so that's another quick check on your calibration curve. But once again, if I was using this to, you know, to do something critical, it wasn't my first go around in lab, I'd redo this calibration curve and get a little better R squared on it. But I'm going to just work the data because this is what I really want to show you is how to take, you know, the first part to let the Excel do the work on this so that you don't make mistakes in the concentration dilutions, because that might have been what had caused this, but we know we didn't make mistakes because the Excel did it for us. And we can kind of read through and double check that. 5 divided to 10, and each time, let's see here, this should be G4. Aha. Actually, we did make a mistake. This is great. This should be 5 mils of the undiluted stock. So, oh, okay. Well, we're working off a G6, so that is correct. And then this one, working off the undiluted stock. So I jumped up and used G4, and there I used G6, but that doesn't matter. All right, just checking. And then this one, I should be using diluting number 2, which is actually position G7. See, there's the G and 7, so that is correct. And that's a G7, so that is correct. So we're going to move on. All right. So this is absorbance versus time, and that's fine. So what I would like to do is turn these numbers, so that is a separate piece of lab data, into absorbance versus elapsed time, which means the first reading is at 0, the second reading is at 1 second, 2 seconds, 3 seconds. So it's interesting that the time coming off this instrument really reads like a clock. So you can look at that. And somebody's got in here and only recorded the seconds on here, so that's kind of helpful. But this is actually clock time, and I can see that up here. So what I'd like to do is read elapsed time. So again, I'm going to let my Excel spreadsheet do all the work. All right? So I'm going to just move all this over a little bit so I have a little room to work, and you're going to see what I'm doing here. Just highlight that, move it just one over so I have a place to work on time a little bit. So why don't I put in here elapsed time? Or I could recall it time, but I'm going to record it in seconds. All right? And so the trick of taking 24-hour clock time and converting it to actual seconds is you think about how many seconds are in 24 hours, and that's 3,600 seconds in an hour times 24. So we'll get out our handy dandy calculator. Go with 3,600 times 24-hour clock. All right, so it's 86,400. So here's what I'm going to do. I'm going to basically say at this moment I'm going to subtract this time. This is a good trick, and you'll learn these things working with time in Excel. It's nice to know, especially that if you want to watch elapsed time. I'm going to reference, I just want to know the difference. So in theory, from here to here, 1 second's elapsed. So I'm going to do the difference. All right. See what I'm saying up here in my formula? The difference between here and here. I don't want to accept, hey, come on, give me a break. I'm trying to get done here. Okay, there we go. And then what I'm going to do is take it times that multiplier, 86,000. And let's see how this works. So that's pretty good. That's roughly 1 second. And now the other thing I want to do is I want to make sure that I always reference the first cell. So when I get here, I'm going to say what's the difference between here and the first cell, and when I'm here, the difference between here and the first cell. And the way you always reference back to the first cell is put a $sign in it. And there you go. And now I can elapse time. Maybe clean that up just a little bit down to a number. There we go. And there's my elapsed time in seconds. And maybe get it down to 2 figures, and away we go. All right, so I'm going to drag this on down. To the very bottom. And then I should be tracking time in seconds along that x-axis and comparing it. There we go. Comparing it to how the absorbance changes. Now, how does this absorbance become concentration? Well, that's what the calibration curve does, right? So what's on the y-axis is the absorbance, right? And what's on the x-axis is the concentration. And so this linear fit tells us how that's related according to y equals mx plus b. So another way I might think about what that means is basically, I'm going to just put this here to remind us that absorbance equals the calibration slope, which is 18,053 times x, which in this case is actually the CV concentration. And then the y-intercept where I started, which is 0.0139. So that's my mathematical relationship. I do a little bit of algebra on that, and I would actually, let's see, put this in brackets, and I could say, well, whatever the absorbance is, if I subtract the y-intercept, 0.0139, and then I just divide it by the slope, 1/8 0.053. Aha, then that actually would spit out the CV concentration. And that's what I'm looking for. So now I have the relationship, and the key is I don't know that relationship till I know, according to the calibration, how absorbance is related to concentration. Now, I could do this calculation for every one of these, what do we got here? Almost 100 entries, and I'll be up all night. Or I could just set it up in the, and let Excel do it for me. And so again, I now have the key. I start with an equal sign. I'm going to say, okay. The first thing I need to do is take my, I'm just going to follow this pattern I've set up here. I'm going to figure out what my absorbance is. I'm going to subtract the y-intercept, 0.0139, correct? And then I'm going to divide it by the slope, which is 18053. And that actually now is reading absorbance, which is very close at 0.45. Should be 2.45 e to the minus fifth. So it's not exactly right, and that's because there's the plus or minus in above the wiggle. As this gets closer to 0.99, this would get closer to 2.45, but we're in the right order of magnitude. So this is great. It's lab data, right? But we also know just, a lot, way too much significant figures in there. So now we're kind of dialing that in. So now what I want to do is I want to just take the log of this. So I go and get my formulas down. It says, well, let's do the log, the natural log, cool, of this, which is my true concentration. And then what I would like to do over here is I would like to take the inverse, which is take 1 and divide it by whatever the concentration is. And there you go. And so now we've done the calculations that we need to do to actually set up our curve. And the beauty of Excel is I can do all three of those calculations all in one fell swoop. Just copy down my formulas. Voila. Now that's done. Now I just need to graph them and see which one seems to be linear. So I'm going to, if I want to just highlight these two columns, I'm going to go Control, Shift, and down arrow, and it'll just find the data at the bottom. And now here's kind of one way you could do this too. I'm gonna get rid of this, and I'm going to show you another way just to do it a little quicker. Let's get time. Let's get all the lines we want. We're going to Control, Shift, downwards. We're going to insert a scatter graph. Now it's got all the trends I want, but they're all jumbled on top of each other. So I'm going to Control X. I'm going to move this chart where I want it. I'm going to go right there, Control V. I'm going to copy it there. I'm going to copy it there. And then I'm going to copy it there. And then I'm just going to walk my way back through each one of these graphs and alter it so it's the graph I would like to work on. So I'm going to start with this one. And if I right click it, I can actually select the data. And so the only ones I want here are so it does have elapsed time running along the bottom, so that's great. And everything else, I want to remove the absorbance. I do want to see how the concentration changes. Remove that. Remove that. Just remove all those. And there you go. Now, got a couple more that hung in there. Remove this guy, remove this guy, and then we'll just watch this. CV versus time. There we go. So there's that graph. This is actually now concentration. Checking for zero order. Right? And there's that. Of course, then I'm going to put, that's the key. It's my elapsed time. This didn't run very long, but that's the idea. You'll probably have runs that are longer, you know, more like minutes instead of seconds. But this is still going to work for what we're going to try and do here. I'm going to select data. Again, get rid of the ones we don't want. We don't want that. Now we don't want this one. We don't want that one. All right, okay. And this guy is checking for first order. Great. And then we'll do this last one. Select data. Remove, remove, remove. Okay. And this last one is checking for second order. Now, you could look at this and say, wow, this looks pretty darn close. This looks really good. It's probably first order by looking, but maybe this one. So the real thing, you know, in this particular case, we know that some of these aren't exactly curved, but in this case, we fit a straight line onto this so that we can let the R squared answer the question. So we're going to format the data series. Whoops. Get in here, highlight that, right click. Let's see here. There's the series. Come here, guy. Back over. Add a trend line. Linear. And really what we're after in this case is the display the R squared. Sorry, I'm going to try and get this back onto your screen. You may not be seeing it right now on Camtasia. There we go. So we're going to display the R squared on the chart. There we go. Get you back up there. Displayed R. We're working on this guy. Displayed R squared on the chart. That looks good. And it's 0.98. Might as well display the equation in case this is the one I'm going to use here in a minute. This guy, same process. Get the series, right click it, add a trend line. Display R squared, put the equation, 0.97. This one, display the series, right click, add a trend line, display equation, display R squared, that over there. So now I'm actually ready to evaluate. I'm going to back out a little so you can see all my choices. So I got the first choice at 963. The second choice, I'm going to have to blow that up a little bit for myself. There we go. 9.8 on the first one, 9.9 on the second one, 9.8 on the third one. So this is a first order equation. And then remember, when you're actually writing a first order equation rate law, you say rate equals, you put in the K, which now we actually have the K, because we can say, oh yeah, rate equals, what is the K? It's the slope of this line, right? Only that's the negative form, but it's 0.0198. And we know that this particular relationship is first order with relationship to the CV, because that's what this graph was set up for first order. And in this case, the hydroxide was a pseudo zero order setup. So this would actually be the rate expression for this particular graph. So I hope this has helped you, and what my point in doing all this is that you should use the Excel or the sheets to do all the hard work for you, is really the goal here. So, and by the way, this looks a little odd. Some of you might be looking at this going, uh-oh, where'd my data go? Well, the problem is there's so many digits they're not seen. Again, both of these should be reported in such a way that they have the proper numbers, significant figures built in. And again, you can do that by adjusting the digits up here on the right or the left once you highlight all these numbers. All right, so anyway, I hope this has helped, and I expect you to be utilizing this. Some of the critiques I'd give about this is if you ever set up a calibration curve in lab, have your computers or your phone or whatever handy, or your graphing calculator, and start graphing the data immediately to make sure it's linear, so you know that you have to redo points if it's not. And then the other thing I would say about it is, I did this quickly so you could just see the ideas, but these graphs are unfinished because they need proper titling. The y-intercept needs to have the trend that it's actually for zero order. It's concentration versus time in seconds. This is concentration in molarity, the log of concentration versus time in seconds, and this one is 1 over the concentration in terms of seconds on the y-axis or x-axis. All right, I hope this helps.